Okay, so now we got another proof to do. Give an inductive proof of the fact that left folding is compatible with list concatenation. Okay, so we're going to prove if we fold something on two lists concatenated, that's the same as folding on the first list, and using this as the starting point to fold on the second list. Okay, importantly, f is a fixed function, and ys is a fixed list. So that means we don't have to like universally quantify f and ys, because that's just like some particular f and some particular ys. Okay? Because normally we would quantify them, but here we don't have to. Okay, state and prove the base case goal. Alright, no worries. So what's the base case? Base case is going to be for all z, this whole statement, but the excesses get replaced with empty lists. I guess if you were like lazy, you could write for all z, p of empty, which is technically, no it's not, because there's already for all z there. There we go. Base case p of empty, I mean, you can probably get away with it. That's technically correct. Okay, what's the left-hand side of p of empty? It's going to be fold L f z empty plus ys. So I guess I should let z be arbitrary. Okay, so left-hand side is fold L f z empty plus ys. Well, empty plus ys is ys by this law here, by A1, by the definition of concatenation. So fold L f z ys. And what I want to get this thing, but with an empty list here. Well, fold L f z empty is the same as z, right? So I could just use f1 backwards on the z. And introduce whatever list I want. Well, actually no, just introduce the empty list. So fold L f z empty ys, which is equal to the right hand side. Cool. All right, no worries. State the inductive hypothesis. Oh, that's basically just p of xs. So it's okay. There you go. Could you get away with writing that? I mean, maybe. You probably really should write the whole thing. So for all z, fold L f z xs plus ys equals fold L f z xs ys. Alright, cool. There's my inductive hypothesis. We'll put him over here. Over there he goes. State and prove the step case goal. Okay, so for the step case, I got to show this statement here for any new x bolted onto the front of xs. Alright, so my step case is to prove for all x, for all z, all that junk all over again, fold L f z x cons xs concat ys is the same as fold L f z x cons xs ys. Okay, so let's prove it. So I guess I'll let x and z be arbitrary. I'm going to start on the left-hand side, like I usually do. So what does this junk look like? I mean, I could use a rule immediately. So I could use A2 and bring the x out the front of the concatenation. I'm going to do that. So fold L f z x cons xs concat ys, which is equal to something, I'm sure. What can I do now? It looks like I can do f2. And so replace the z with fzx. Okay, I'll do that. Whoopsies, what rule? This was A2. Don't forget your rules. Oh, I forgot my rules earlier. Bad David. That's left-hand side, that's A1, and that's F1. Yeah, don't forget your rules. Okay, let's continue with this. So this becomes fzx, and then xs concat ys by some magical rule, F2. And now this looks like my inductive hypothesis, because in the inductive hypothesis, it works for any value of z. So it's going to work for this whole value of z. So I can replace this thing with this thing. I'm sorry, that's not my inductive hypothesis. This is my inductive hypothesis. This term here looks like this term here. So I can replace this with that. But this z is our fzx. That's totally okay. So let's do that. So we're going to get fold L f, fold L f, instead of z we have fzx, xs, ys, by inductive hypothesis. And now I've got to make this look like that. So how am I going to do that? Well, it looks like I can use f2 backwards. I can sort of pack the x back into the list on the junk on the inside. So fold LF. Yep, take the x and put it back on the list. So fold L F Z x cons xs, and then the y's on the outside by rule f2 backwards, and that's what I want. This is precisely the right hand side. Cool. Is there any more to question? Nope. Okay, that's enough for this question. Move on to the next one.